Hello all. Welcome to the eighth session of the online session on solving problems for the geometric design course. This, as I used to say every time, this course is between 6 to 8 p.m. every Monday. Okay, you can ask your questions here. We will be discussing about previous year's assignment problems and also some concepts related to that. Okay. So let us begin the session now. Okay. If you remember, last week we were discussing about horizontal curves, okay, the introduction of super elevation and the equation for radius of the curve and so on and so on. This week, and we were solving problems related to that. Yes, from last week, I introduced a new way of giving the concepts. Like earlier, we used to discuss the concept for the first 1 hour, and later on, the second hour, we will be solving the problems. But from last week, I changed it to solving the problems as and when, solving the problems and explaining the concepts as and when it is required. So just feel free to give your comments on that. Okay, um, to begin with, okay, last week we did not complete the entire set of questions. We had something left behind. Okay, uh, we were yet to talk about um, extra widening. Okay, so from this in this session we will start with last week's portions, okay, which was left behind, and then we will proceed to this week's portions. Okay, so okay, we were solving a problem, okay, and in that problem, we were asked to solve, we were asked to find out, we were asked to design the super elevation for that, for a particular section of a road, okay, for a horizontal curve, okay. So we solved all that, and the last question, okay, was to find out extra widening. After finding out the super elevation requirement of that particular section of the horizontal curve, okay, or of that horizontal curve, the last session was to find out extra widening. So, since it was a new concept and since we were running short of time, we brought it to this week. Okay, so we will begin from that. Now, a horizontal curve is laid on a, it is the same question as we did last week. Okay, so a horizontal curve is laid on a two-lane, 7-meter wide major district road in plain terrain. The radius of the curve is 250 meters and the vehicles are moving at a speed of 80 kilometers per hour. Assume the length of the wheelbase as 6 meters. Okay, now we are asked to find out the how much extra widening is required. So before that, we will see what extra widening is. Okay. So, if you see, this is the straight section of the road where the road is straight. Okay. After that, when you want to change your alignment, okay, from this direction to this direction, the horizontal curve has been introduced. We saw the reason for introducing horizontal curves. It is to change the alignment of the road, right? Now, we also saw that in this horizontal section of the road, there's something called as super elevation. Yeah, the road cross section will be something like this, as opposed to this in a straight section, right? In straight section, your cross section of the road will be something like this, which is called as camber, and in the curved section, it will become super elevation. Like only one portion of the roadway will be raised, okay, because we saw that vehicles will be tend to be pulled outside when negotiating a curve, and hence the introduction of super elevation. We also saw one more concept that in the horizontal section of the curve, the width of the roadway is slightly increased, and this increase in the width of the roadway in the horizontal section of the curve is called as extra widening. And there are two reasons for providing this extra widening. Why the width of the road which is W, has to be increased to something called W plus WE. So this is the extra widening. You're providing an extra widening of WE. We will see why it is required. Okay. So one reason is because of a rigid wheelbase. If you see this figure, you will understand why. So if your vehicle is here, your rear wheels, this is the rear wheels at the rear end, at the back end, right? And this is the wheels at the front end. So the wheels at the rear end will exactly follow the wheels at the front end in a straight portion. But when you try to move along a curve, so let me go to a new slide. Okay, when you try to, okay, thank you so much for letting me know. I'm really sorry. Okay, I'm really very sorry. Okay, so I was talking about a problem in which we were asked to find out, in which we are asked to find out extra widening. I was telling why, what is extra widening, and we were moving on to why it is required. So if you see, this is the straight section of the road, and it has a width of W. Okay, but when you go along a horizontal curve, its width is kind of increased, and this increase in the width of the roadway on a horizontal curve is called as extra widening. There are two reasons for providing extra widening, and we will see why. Okay, so if you see in this figure, this is a straight section, and if my vehicle is in this straight section, if you consider this as the wheels on the rear end, and if you consider this as the wheels on the front end, okay, on a straight section, the wheels on the rear end will exactly follow the path of the wheels on the front end because it is a straight section, right? Your vehicle is like this, and it is exactly behind. So the wheels at the back end are exactly behind the wheels in the front end. So on a straight section, they will exactly follow one. Rear end will exactly follow the wheels in the front end. So no issues. Whereas when you traverse on a horizontal curve, if you see, if you see this pic, here also, the wheels, so this is the wheels in the front end and this is the wheel in the rear end, right? Here also, the wheels in the front end will exactly follow the wheels in the rear end, okay? It will not bend like this, okay? So to make it clear, this is my roadway and this is my vehicle, okay? So this straight portion, which is called as chassis, is rigid. Rigid as in when you're trying to traverse on a horizontal curve, your vehicle will not bend like this, right? Because your vehicle is a rigid body. Because of that, this rear end will be thrown out, will exceed the width of the curve. Okay, that is what you see here. So this is the width of the horizontal curve, which is as the same width of the straight section, right? But when it tries to traverse, when it tries to make a turn, since this body is rigid, this vehicle is kind of thrown outside, right? If the body was flexible, imagine, okay, if it was if were it been flexible, then it would have stayed in the same lane, but the body is rigid, so this outer wheel is kind of thrown outside. In order to accommodate this only, the width of the roadway is increased. So you kind of increase the width of the road. This widening is called as mechanical widening. Okay, just a second. Yeah, this widening, which is required in terms of the because of the property of vehicle is called as mechanical widening. There is one more widening which is called as psychological widening. Now, what is the psychological widening? Now, when you try to traverse on a curve, you will always try to stay in the center of the curve. Okay, when the vehicles on the inner lane will try to move towards the center, and so all the vehicles will try to move towards the center, okay, to have a better visibility, right? And because of this reason also, your curve has to be a bit wider, okay? So that widening is called a psychological effect, a psychological widening, because it comes from you, from your perspective, from because it is not required, but you have a feeling to move towards the center of the curve. um, so it is just an intuition, so you require a wider width because of your intuition, and that is why that is called as psychological widening. So this extra widening has to be a summation of this mechanical widening and this psychological widening. Okay, so it has to be um, a summation of these two. Now we will see how to find out mechanical widening and how to find out psychological widening for this problem. But before that, we will see how this equation. So for psychological widening, you do not have a proper um, theoretical background to it. You have only an empirical equation. So that equation we cannot define, right? But for a mechanical widening, since it is based on the dimensions of the vehicle, that equation can be kind of derived. So that we will see how the equation of mechanical widening is obtained. Okay, so let us take a vehicle. So this is my this is my pavement. Okay, and this is my vehicle. So it will be, this wheel will be kind of turned. This also will be, because you're turning the steering, right? Whereas the back end, and this is my the this rigid base which connects the two axles. So this is the front axle and this is the rear axle. This is called as chassis, and this has a length of L. Okay, if you see this vehicle, this wheel is thrown out, right? Yeah, this wheel is thrown out. So this much extra widening has to be provided. Now how will you find out this extra widening? So this is the extra width that is provided. Okay, so how will you find out this extra widening? So if you, so this is a horizontal curve, right? So it will have a radius. Now if I take this radius as R2, and from this, if I take this radius as R1, okay, if you see, I'm not drawing it correctly, okay, but this will form a right angle triangle. Okay, this will form a right angle triangle, and this length is L. I should have shown you a better picture, but since I'm drawing, it is going here and there. So if you take this separately, okay, it will be something like this. Right? So this is R1, this is R2, and this is L. and this will be WE. Okay, this entire distance is R2. So this is what you will get from this figure. Okay, now using Pythagoras theorem, you can write R2 square as L square plus R1 square, right? And this R1, we just saw that this R1 is nothing but R2 minus this mechanical widening, the whole square. Okay, now I'm going to expand it. So R2 square is equals to L square plus R2 square plus WE square plus, minus 2 R2 WE, right? Now this and this will get cancelled. So if you take WE, it will be 2 R2 WE minus L square. Just a second. Sorry. Yeah, you can take this out, right? Is equals to L square. WE, if you take this out, it will be WE minus 2R2 is equals to minus L square. So WE will be equal to L square by 2R2 minus WM. Yeah, so this is the equation for finding out mechanical widening. WM or WE, both is the same for this case. Okay. Now this is for if the lane width is 1. Sorry, if there is only one lane. Number of lanes is 1. If you have n number of lanes, you simply have to multiply this by n. Okay. So this is the equation for mechanical widening. This is not the final equation because the final equation, it is see, if you see here, it is kind of like an implicit equation. Yes, implicit equation, because you have Wm on this side as well as Wm on the other side. So if you approximate, we wrote R1 is equals to R2 minus Wm, right? But if you take R1 to be more or less equal to R2, since the radius is very large and Wm is very small, you can kind of neglect this. But if so, when you do that, you will get this equation as NL square by 2R. Okay, so this is the final equation for mechanical widening. Okay, it is enough if you remember it, but I simply wanted to show how this has been derived. Okay, so this is mechanical widening, and we saw that psychological widening is just an empirical formula. So we will see psychological widening as well. So that equation is nothing but .1 V by root R. Okay, where V is in kilometers per hour and R is in meters. When it is an empirical equation, you should always remember the units of the parameters that have been used in the equation. Why is that? Because since it is empirical, its units will not match. So what is the unit for psychological widening? Since it is just the width, it has units of length, right? So it should be in meters. But if you see, if you find out the dimensions of this entire term, it should come to meters had it been uh, had it been had it had any theoretical background to it, right? So if you derive the equation like for mechanical widening, its dimensions will be matched. But since it is an empirical equation, you should remember the units because the dimensions won't match, and it is important for you to substitute the parameters as per the units that has been given for the equation, okay, as per how the equation has been defined. Now we will see for this problem how this extra widening is calculated. So we'll go to the question. What and all information do you have? You have N as 2 because it is a two-lane road. The width of the road is 7 meters. Maybe this is not required. Radius of the road is 250 meters. And speed V is 80 km/h. And one more thing is length of wheelbase. It is 6 meters. Now what is mechanical widening? It is nothing but NL square by 2 into R, which is 2 into 6 square by 2 into 250. Okay, and this is psychological widening. So you have to find out the value for this. Now what is psychological widening? We saw it is zero point 0.1 V divided by root of R, where V is substituted in kilometers per hour and R is substituted in meters. So it is 0 0.1 into V is 80 kilometers per hour divided by root of 250. So if you now you have to add, so the total extra widening will be mechanical widening plus psychological widening, which will be 0.65 meters. I will be happy if you calculate the answers and let me know. Okay, for mechanical widening and psychological widening, maybe in the next class, please try to bring calculators. We will solve so that the session will be interactive, because it is not a big question, right? So it is just a simple math and you have calculator in your hand. So it will be kind of interactive if you bring a calculator and we will solve the problem together. Okay. So the answer for this is 0.65 meters, right? Now moving on to the next question. They've asked an expressway is passing through a rolling terrain having rainfall intensity of less than 1000 mm per annum. Considering the rolling design speed, the radius beyond which no super elevation is required would be what? See, if they say that no super elevation is required, it doesn't mean that your road is straight like this, okay, on the horizontal curve. You should provide a super elevation, minimum super elevation of gradient equal to its camber. Okay, we saw camber, right? And we saw that it is 2% or 2.5%. We saw something like that. When they say no super elevation is required, it doesn't mean that your road has only camber or it is perfectly flat like this. It means that you have to provide a minimum super elevation equal to its camber. Okay. Now, since they have mentioned that, for this they have mentioned that no super elevation is required, and just now I told you that even if they mention it like that, you should provide a super elevation of gradient equal to its camber, right? So for this road, you need to know what is its camber to find out the radius. So radius depends on um, speed, super elevation, and friction and acceleration due to gravity, right? So it depends. So the formula depends on all these. Now, um, if you say that no super elevation is required, and I'm telling you that you have to provide a minimum super elevation of camber, the final R which you find out using this minimum super elevation is called as the minimum radius. Okay, and this radius, so if you provide like this, your friction and all won't be taken into account. You remember solving the problem um, for design of super elevation, the same formula. So v square by 225 into c, where this 225 will take into account of converting v from meters to kmph and g as 9.81. Right? See, if you so this is also not an empirical equation, but since um, I'm converting meters to kmph and I'm substituting for g as 9.81, I should, for this formula also, I should remember what should be the units of the various parameters that I'm providing. Now, it is not at all necessary for you to by heart this equation, by heart the number 225 and all. You simply have to write the equation for the radius, which we saw r is equals to v square by g into e plus f. You have to simply substitute for this in this equation. You have to substitute for v in the exact units, right? You can substitute for v from kilometers per hour. You have to convert it into meters per second because g is in meter per second square and e does not have any units, right? So you have to substitute for the um, parameters with the proper units, or you have to by heart the formula by where the units have already been converted. So this, keeping this aside, this is just some additional information. So for this problem I told you that you require something called as the camber. What is the camber to solve this problem? And the equation to solve this problem is this, right? You simply in place of super elevation you substitute for camber. That's it. Okay. So they have said that it is an expressway and it has a rainfall, so it is in a rolling terrain and it has a rainfall intensity of less than 100 mm per annum, right? So for this problem, the camber is 2% because for less than 1000 mm, so this is a cross flow, so this is an expressway, and for less than 1000 mm per annum of rainfall, the camber required is 2%. This information has been taken from the session where we talked about camber, okay, cross slope or camber. So you should remember that also, everything is interlinked. So now you know that camber is 2%. So now simply you have to substitute it in this equation. So R is equals to V square by 225 into, how will you substitute for camber? If it is 2%, you will not substitute it as 2 as it is, you will substitute it as a decimal. So it will be 0.02, nothing but 2 by 100. Okay, the percentage you are converting it into a fraction. So what is V? V, we saw that it is, yeah, they have not given V also, but they've given you one more information that it has a rolling, so you have to consider the rolling design speed and it is a rolling terrain. We saw that the speed of a roadway, I mean, the speed of vehicles on a roadway will depend on the type of highway and the type of terrain. So for solving this problem, you require two information. One is the camber, okay, which we just saw, and one more is the design speed, which you can take it from the table. Okay. If you see, I have not shown this table here, but we have already seen what should be the speed of vehicle for an expressway, okay, expressway and in a rolling terrain. So its speed is close to 100 kilometers per hour. So V is 100 kmph. Now substitute it in this equation. So it is 100 square by 225 into 0.02. Okay, and this will be nothing but meters. Okay, so this is the final answer. What is this answer? It is the radius. Okay, when no super elevation is provided and on an expressway, um, on a rolling terrain. Okay, so this is the radius. Okay, now the final, sorry, it's not the final question. So this is regarding the attainment of super elevation. We saw that in a straight section, the cross section will be something like this, and we call this as camber. In a horizontal curve, its cross section will be something like this, which we call it as super elevation, right? Now, how will you introduce the super elevation to the pavement? Your pavement is like this, right? Has a cross slope like this. Now, if you take this as my roadway, where this is the horizontal curve and this is the straight section, it has a cross slope of camber here and it has a super elevation here. Okay, the super elevation kind of starts from here at the beginning of the horizontal curve. Now, how will you introduce the super elevation? Do you think that till this point you can provide camber and after this you can simply jump to super elevation? You can simply convert the cross section to a triangle, a right angle triangle from this point to this point. It is not possible because your vehicle, you have to introduce it smoothly for the vehicle. Okay, you should not even able to you should not be able to realize the transition that is happening. So what I mean to say is, if this is my straight section and this is my curved section, okay, so till this point, from this point, it is going to have a cross section of super elevation, and before that it should have a, in a straight section it should have a camber. In between this, you should introduce a gradual transition from this shape to this shape. Okay, so you should not introduce it suddenly. So that is called as, so that concept is called as attainment of super elevation, and there are ways of doing this. There are okay, so we will see how this is implemented. So first, what they will do is, my cross section is like this. From this, you have to bring it to this. You know that this has already been, so this is already slanting. So this you will leave it like that, and you will try to bring this slope to a flat cross section like this. So this triangle you will convert it to something like this. Okay. So earlier it was at this dotted line. Now this dotted line you are bringing it to a flat point. Okay, flat section. So this is known as tangent runout. Where will you do this? You will do it in the straight section itself. Okay. So in the straight section, your cross section at this point is a triangle, and after some point, it is going to change like this. Okay. So this distance that is required is called as tangent runout. And this, during this tangent runout, your section will be straight. Okay. It will not have any transition or it will not have any curve. Now, there's something, so there's kind of a change of alignment, and after this, you have your curve. Okay, my curve starts only at this point. So this is my horizontal curve. Okay, then what do you think this will be? We already saw from a straight section to a curved section, you should not, most in most cases, you should provide a transition curve between these two. And we saw the reasons for transition curve as you should be able to introduce the radius smoothly. So here the radius will be infinity and here it will have a radius of r. So you have to provide a gradual transition. So here the centrifugal force will be zero and here it will have a centrifugal force, right? It will be pulled outwards. So that also should be gradually introduced. One more reason that we saw is the super elevation from cross slope to camber, sorry, from camber to super elevation, it has to have a gradual transition, just like we saw now. So for that, you require a transition curve. And one more also, you have to provide extra widening as well, right? So in order to introduce extra widening also, you will provide a transition curve. An example for this can be seen in this figure, where you see this is your horizontal curve. So this is your circular curve, and this is your transition curve. Here itself, you have started introducing the extra widened portion, right? So for this reason also, you will provide a transition curve. Now, I told you that in this figure, this distance is called as tangent runout. Okay, so here your cross section will be a triangle like this, and this distance, right, is called as super elevation runout. Okay, so this is where you're from the straight portion, you are going to take it again slanting like this and make it a triangle. Okay, this straight portion has to go up, right? So from this, it has gone up to a zero slope. Okay, the slope is zero, right? And from this, it has to go to, so it has to go up and become a triangle like this, right? So this distance, so where you provide this transition from zero slope to a super elevated slope is called as super elevation runoff. Okay, and this is where your transition curve will start, which means your transition curve will start only from this point, is only from this point to this point. Okay, this tangent runout, you will not include it in the transition curve. Okay, so now they have asked you one question. So we will see this 15th question first. Super elevation runoff distance is donated by what? So if you see here, at this point A, it has a camber like this. And after that, this has been made zero slope. Okay. And you know that this distance is what we saw as tangent runout. It happens in the straight section. Now from this, it has to come to a slant like this. And from this slant, it has to kind of rotate. We will see this now, but just remember that from this to the final, from this zero slope to the final super elevated slope, this is called as super elevation runout. So what is that? BD will be my super elevation runout. Okay. Now I told you. So so based on my explanation, you would have thought that BC is my super elevation runout, right? So many of you would have felt that. Why did I say that BD is the super elevation runout and not BC, even though this slant has already been attained here? Does anyone does anyone want to try to answer this question? Okay. So yeah. So I told you. So this is A, this is B, this is C, and then there's one more, D. Okay. So if you see, this is tangent runout. This entire is super elevation runout is what I said for the question. But when I explained you, I told you that this has to just move up and it will become a triangle like this, which is the which looks like a super elevated section. But still, I did not say that is the super elevation runoff. I told that BD is the super elevation runoff. Now, if you see clearly, you will understand. This has a, so this is camber, right? And this has an angle of, let us say, it has an angle equal to C. Okay, say this can be 2 or 2.5%, right? Now, this also will have a slope of C, right? Now, when I try to take it up, okay, and form this as a triangle like this also will have a slope of C. But what is my super elevation? This slope will be just 2 or 2.5%. But what is super elevation? Super elevation is usually, so if I take this as E, super elevation, let us say, for example, and I'll take it as 7%. Okay. Now this is only 2%. Here my entire super elevation has not been achieved. Though the shape of the super elevated portion has been achieved, its value has not been achieved because this is just 2% slope. Now I have to take it to 7%, only then at the start of the curve. So only then the super elevation for the curve has been attained, right? If the curve requires a super elevation of 7%, then I have to provide 7%. So till I reach that 7%, I will keep increasing this, right? So earlier it was here, it was just 2%. So I have to keep increasing this. Now it will become 7%. So till then, it is called as, so till then you will provide a transition curve, because transition curve you will provide it from so at the end of the transition curve your horizontal curve will start, right? So when your horizontal curve starts, your super elevation should be equal to what is required for the horizontal curve, right? So this entire uh, B to D distance will be transition curve, and this is called as super elevation runoff. Okay, I hope you understood this. So that is why I said BD is the answer for this and not BC. Now, final super elevation on the carriageway is attained through what? Okay. Now we saw, so let us see how this is attained. Now we saw um, two ways. I mean, two ways, and as in two steps. Sorry, instead of ways, let me call it as steps. Okay, to attain super elevation. So the first step will be I have to so this is called as reverse camber. I have to remove this reverse camber. Okay, so I have to remove this reverse camber and I have to make it to a triangle like this, right? I can do it in two ways. If I have a camber like this, I can increase it like this. First, increase some height here, then again increase some height, then again increase some height and bring it in par with this slope. This is one method of doing it. So this is one step. This is the first step. First step is removing the reverse camber and making the slope equal to the slope of the camber. Okay. So either I can keep on increasing this slant, I should take it up and up till it reaches the slope of the camber, or I can do it in another way where, so if this is my thing, I have to take it like this. I have to increase, I simply have to add materials so that this has been achieved, right? So I can do it in two ways. Okay, so this till here. Okay, so I can either increase this edge of the roadway, or I can increase, so this topmost point is called as crown, so either I can increase this portion and make it a triangle like this. Now this is step 1. Why is it step 1? As I told you earlier, only the shape has been attained, but the entire super elevation has not been attained. So this has a slope equal to the slope of the camber. Let us call it as C percentage. Okay, so this is step 1, where I will remove the reverse camber, I will eliminate it and um, make it have a slope equal to the slope of the equal to the camber of the roadway. Okay, so this is step 1. So what is step 2? Step 2 is from this camber C, so this is has a slope of C, I have to make it to E, right? So this has a slope of C, I have to make it to E, so the slope has to be even, sorry, steeper. Okay, so this is called as step 2. So I require two steps in um, two steps in attaining the super elevation. One is I should remove the reverse camber and make the slope equal to that of the camber, and then from that I have to increase the slope to from C to E. Okay. Now this will be achieved in, so I told you there are, so I will draw a flow chart. So super elevation attainment. It requires two steps. Step one, step two. Step one is I have to remove this reverse camber and make it like this with a camber equal to C, with a slope equal to camber. Now step two is I have to make this C to E, which is the slope of the super elevation. Now this we saw that it is achieved in two ways, two methods to achieve it. One is I will raise the outer edge, right? I will raise the outer edge and make it like this. And the second method is I will raise the crown. Okay, this crown portion, I will raise it and make it like this. So there are two methods of attaining this step one. There are three methods of attaining this step two. So what should I do? I have to simply increase the slope of this, right? I have to increase the height of this slant. I can do it in two ways. Either, um, so imagine holding a divider. We know a divider, right? So it is kind of like a compass, but it has sharp edges on both sides. So imagine that this is the um, connecting point of the two needles. Okay. So either I can simply rotate this arm and increase the height like this. Okay. So this is called as, so if this is the inner edge of the roadway, okay, I will call it as rotating about the inner edge. Okay. So that you can see it from this figure. Okay. So this is rotating about the inner edge. Now there's something called as rotating about the outer edge. Okay, so so a roadway will have an inner edge and outer edge. So either you can rotate it about the inner edge, you can increase the height about the inner edge, or you can increase the height about the outer edge. Okay, so if this is my outer edge, so already my camber is like this, and this is my outer edge. So how will you increase the height of this by holding this constant? You have to further dig further and make the roadway. So you will remove this portion of the soil which is here. Okay, so this is rotating about the outer edge. Okay, so one, you have to raise it so that you will add extra material here. So if this is one edge, okay, and if you're rotating about the outer edge, you have to remove excess material here. Only then you will get the required slope, right? Or you can do it in another way where you can rotate it about the center. So if this is my C%, I can keep this point constant and rotate it like this, which means I will add some material here to increase the height of this, and I have to remove some material here to decrease the height of this. Okay, so step two can be achieved in two ways. One is rotating about the inner edge, rotating about the outer edge, or rotating about the crown. Okay, center line. Okay. So this is what I was talking about, the three methods. Okay, so these two is for step one, methods for step one, and these three other methods for step two. Now, if we go and see the question, okay, final super elevation on the carriageway is achieved through what? Rotation of pavement about center line, rotation of pavement about outer edge, rotation of pavement about inner edge, or none of the options. this is pertaining to this question. Okay, they've asked how this has been achieved. So I will, okay. So if you see, this is my center line, okay, and this center line has remained constant, right? The center line is constant. I mean, center point is constant, which means they have rotated about the center point. So the center point remains the same. They have only lifted this portion and reduced this portion. So for this question, the answer is the pavement has been rotated about the center line. Okay. Now moving on to the final question for last week. A horizontal circular curve is directly starting from and ending at straight sections. So yeah, actually this is a wrong figure. As per this question, there is no transition curve for this question. So the straight section, from the straight section, it immediately becomes a horizontal curve, and from horizontal curve, it again becomes a straight section. There is no transition curve in between. So we saw that we introduced this super elevation, or we introduced this extra widening gradually through the transition curve, like this, right? But here for this question, it does not have a transition curve. So how will you introduce extra widening? So this comes under implementation of how will you implement the extra widening. So for that, what you will do is, um, just a second, right? Two-third. So if your extra widening widened width is WE, you have to introduce this extra width, two-thirds of this. Okay, two-third of WE. You have to introduce it gradually in the straight section itself. So you will gradually at a uniform rate, okay, increase it. Okay, so at the end of the straight section, your entire width will be W plus 2 by 3 of WE. Okay, and remaining one third you will provide it after the circular curve has started. So you will kind of increase it, and after that, so this is where, so by this point maybe the entire super elevation has extra widening has been attained. So from this portion, okay, your entire width will be W plus WE. Okay, so the remaining one third of the width, okay, here you have provided only two thirds of the extra widening. Here after the circular curve starts, you will provide the full extra widening by adding the remaining one third also. Okay, so if you see here, the answer to this will be, yeah, so they have asked the percentage that shall be attained on the circular curve. So what is the percentage? 1 by 3 into 100, which is 33.33 percentage, right? So how much percentage of extra widening will be provided on the horizontal circular curve? It is one third, which is 33%. Okay. Now moving on to this week's problems. Okay. Now we will see in detail about so in this week, sir would have discussed about transition curve and gradients. Okay, vertical curves, summit and valley, which is summit and valley curves. So transition curve, we know one thing about transition curve. We saw the need for transition curve, and we saw why it is required. Sorry, both mean the same. Okay, so we saw the need for the transition curve. Now, what should be the length of this transition curve? Okay, so this, how will you find out this length is? You already know the need for introducing the transition curve. So based on the need for introducing this transition curve, okay, you will find out its length. So for example, there are three equations to find out the equation for transition of there are three equations to find out the length of the transition curve. Okay, so we will see what are they, but before that I told you, so in order to understand the three equations, we first need to know the, again we'll go through again the need for the transition curve. So transition curve is gradual introduction of centrifugal force. Okay, gradual introduction of super elevation. Okay, so keep these two in mind. So based on these two only, the equation for the length of the transition curve has been derived. Okay, so you need to introduce, so this centrifugal accelerator force is nothing but it will produce a radial acceleration, right? This force will produce a centripetal acceleration. So this has to be gradually introduced. So if this is my straight section and this is my curved section, okay, horizontal curve, this is my, so this is my transition curve, and say it has a length equal to ls. Now this ls, okay, this length will depend on the rate of the rate at which the centripetal acceleration is introduced. Okay, so so in order to know that, first let us see what is the equation for centripetal acceleration. So the equation for centripetal acceleration is v square by r, right? We already would have seen this equation in solving last week's problems where we derived equation for radius of curve, right? Now what is the rate of change of centripetal acceleration? So if this is the centripetal acceleration, rate of change, if anything comes with the term of rate of change, it means that the variation of that quantity with time. So the rate of change of centripetal acceleration is c by t. Okay, so okay, let me take this as a. So a by t, so rate of change of centripetal acceleration c is equal to a divided by t. Now this t, you can substitute it in terms of length and velocity, right? You know that velocity is equals to change in length by change in time. Rate of change of length, rate of change of distance is your velocity. Now substitute for this t here. Okay, so c is equals to a divided by, what is t? T is L by V. Okay, now substitute for a also. If you substitute for that, you will get V cube divided by R into L, right? R into L. Now this L, so C is equals to V cube by R into L. Now this L is what you want. This is the length of the transition curve. So V cube by C into R is the equation that is derived based on this concept of rate of introduction of centripetal acceleration, right? Sorry, centrifugal acceleration. So to repeat that, the centrifugal force is V square by R, and you are supposed to find out the length pertaining to the rate of change of this centrifugal acceleration. So in order to do that, you will substitute for where you so rate of change always includes time quantity, and this time has to be substituted by length and velocity, where this length is nothing but the length of the transition curve. Okay, so if you rearrange the curve, you will get this equation. So this is equation number 1. This you will call it as length of transition curve based on rate of change of centrifugal acceleration. Okay, now to find out this C, you have an empirical formula, which is AT divided by 75 plus V. You should remember that I told you that if it is an empirical formula, you should remember the units, right? So this V, it has units of kilometers per hour, and the range of the C is between 0.5 to 0.8. Okay, so if it exceeds 0.8, you should take it as 0.8, and if it goes below 0.5, you should take it as 0.5. Okay, so this is the range for rate of change of centrifugal acceleration. So this is equation number 1. Now moving on to equation number 2. So what is the second need in order to introduce the um, super elevation gradually? Right? Just a second. Yeah. So at this point, it is going to have a camber. At this point, it is going to have a triangular section like this with a slope of camber, and at the start of the horizontal curve, it is going to have a triangular portion like this with the slope of super elevation, right? So this is where you will call it as transition curve. Here it is called as tangent runout. Sorry, tangent runout and some portion of super elevation runout, right? So you have to find out how to introduce this, at what rate I should increase the slope of the super elevation. Okay, so that is called as rate of change of super elevation along the length. As I move, so what it means is, as I move along the length of the curve, length of the transition curve, how should I, at what rate should I increase this slope? I should keep on increasing, right? So here it was C and here it will be E. So how, at what rate should I increase the super elevation height? So that is called as rate of change of super elevation. Now, how will you do that? So what is the equation for that? Okay, so what is rate of change of super elevation? Let us take a rate of change of super elevation as E divided by L. So this is rate of change of super elevation along the length. So with each passing distance, what is the change in super elevation? So this is nothing but, let me take it as 1 by n. Okay, so this is also kind of like a slope, right? So this is taken as 1 by n is equals to E into L. Now how will you find, so this is the length of the transition curve, because as you move along the transition curve, how will you introduce this super elevation? Okay, so this L, if you just rearrange it, you will get n into E. Okay, now this E, you have to substitute for this E. This E is in percentage, right? You have to substitute for it in terms of height, because it is the height you are introducing, right? So if this is my E percentage and this is my width of the road, okay, based on Pythagoras, trigonometry, you can find out what is this H. So it is the rate of change of this H that has to be introduced here. So you have to substitute, instead of E, you have to substitute for H, okay. It actually has to be H by L only and not E by L. In order to make you understand, I wrote E. It has to be H by L. So this H is nothing but, let us say, tan theta is equals to opposite by tan theta or tan E. Okay, this theta, this E, I'm substituting it as theta. H divided by W. Now, so if theta, since theta is very small, I can take tan theta as theta, so it will be H by W. Okay, so LS is equal to I have to substitute for h, right? So this is h. So w into e into this slope n. Okay, so this is the final equation for super elevation, transition curve using the second criteria. Now this, instead of this w, it should be w plus we, because this entire width, including this including the extra widening, it will be w plus we, right? So it has to be w plus we, and this is for introducing the rotating the pavement about the inner or outer edge. We saw about rotating the pavement about inner or outer edge, right? So this is the equation for rotating the pavement about inner or outer edge. Ls is equals to n into e into, so w plus we. Okay, so now if you're rotating about the center, okay, you have to multiply this by 0.5. Okay, I hope you understand, because see, if you increase, so if you take theta here and find out what is h, okay, the same theta, if you rotate it about this edge, the same h, okay, it will be achieved here as well as here. Okay, so the length of the curve will be reduced to half, okay, when you rotate it about the center line. Okay, so you just have to remember that for this equation, if it is rotation, if the if the section is rotated about the inner or outer edge, it should be just this equation, whereas if it is rotated about the center line, then you have to multiply it by 0.5. Okay, so this is one more criteria for finding out length of the transition curve. Now there is one more formula, which is empirical formula. Okay, so you have, it is just an empirical formula, so it is 2.7 v square by r, or v square by r. So this is for urban roads, plain roads and rolling terrain, whereas this equation is for hilly terrain. Okay, you have to use the appropriate equation based on the topography. Okay, so now you have three equations for finding out the equation of the transition curve. Now what will be the final equation? So for safety, you have to take the maximum of the three equations for as the length of the transition curve. Okay, so if you're asked, if you've been asked to find out the length of the transition curve, you should find out transition curve based on these three criteria and take the maximum of the three. Now for this question, okay, they have asked particularly, to find out, sorry, not this, yeah, they have asked you particularly to find out the length of the transition curve based on rate of change of centrifugal acceleration. Okay, now let us substitute and find out the answer. So what is given? N is equals to 2, radius of the curve r is equals to 70 meters, design speed v is equals to 45 kmph. Okay, so what is the equation to find out length of transition curve based on based on the rate of change of centrifugal acceleration, centrifugal acceleration, it is nothing but v square by c into r, right? We don't know the value of c, but we know the formula to find out c. We know that c is found out by this empirical formula, which is 80 by 75 plus v. Okay, this v you have to substitute in kmph, so 80 by 75 plus 45, which is nothing but 0.667. Okay, it is between 0.5 and 0.8. Okay, so the value of c is 0.667. Now if you substitute for 0.667 here, substitute for V as 45 kilometers per hour. Here you have to convert it to meters per second, okay? Because we have derived this equation is not empirical. And R you have to substitute it as 70 meters. So if you do that, you will get the final equation as 41.962. So this is the equation for the transition curve. So there is also, as we saw, there are also equations available where they have substituted for this V, um, for this conversion of V to from kmph to meters per second, and that equation will be Ls is equals to 0.0215 V cube by Cr. In this equation you can substitute V as kmph, but here if you take the exact equation without changing anything, then you have to substitute V as meters per second. Okay. Now moving on to the next question. So the value of deviation between circular curve and transition curve at the center of the transition curve would be what? So what is this deviation that they are talking about? Now we know that this is the straight section. If your transition curve is not provided, this will be my curved section, and this again will be my straight section. So all this will come under the same center line, right? Whereas if you provide a transition curve, okay, so see till here, it is a straight section, okay, from here it is a straight section. From here to, from this point T to this point E, it is transition curve, okay. So this is transition curve. Now, if you provide a transition curve, your curve has been shifted inside, okay. Without this transition curve, if you see, if you take this entire section to be a straight section, and from here if you take draw a horizontal curve without a transition curve, it will come along this dotted line. Whereas if you provide a transition curve, the curve will be shifted inside. Okay, this shift is called as deviation or shifting of the horizontal curve. Okay, so this shift, they have asked you to find out this shift. How will you find out the shift is this, the value of this shift is also an empirical formula. Okay, so this is also an empirical formula. So if you take this distance shift as S is equals to L square divided by 24R, where this L is nothing but length of the transition curve. So they've given the length of the same problem only. Okay, so this question is for problems 1 and 2. Questions 1 and 2. So what did we find out the length of transition curve as? 41.962 square divided by 24, and what is the value of R? It is 70. It is given in the question, and this will be 1.048 meters. 1.048 meters. Okay, so this is the final value for shift of the horizontal curve introduced because of the introduction of transition curve. Okay. Now this question stands for questions 3 and 4. Okay, so a two-lane national highway is laid in a hilly terrain. The radius of the curve is 70 meters. The length of the transition curve is, so radius of the curve is 70 meters. Length of the transition curve is 42 meters. Shift of the transition shift is 1.05 meters. Deviation angle is 55 and designs. So I'm just writing the information. This is nothing new to us. But what they've asked, well, when we read what they've asked, I will try to explain. I will explain the concept. Okay. Deviation angle, we all know. We saw it in the last class also. So it is 55 degrees. Okay. Now, let us take the same figure. They've asked you to find out length of the transition curve. Okay. let me draw a situation without, sorry, length of the circular curve. Let me draw a situation without a transition curve. Okay, we saw this in last class. So this is my straight section. Okay, from this point, my circular curve is starting. So what will I do? I will extend this tangent here. I will extend this tangent here. So this is my deviation angle. And what did we see? If this is my entire circular curve with length of L, this will be my deviation angle. Okay, if this is my deviation angle here, this is going to be my deviation angle. So how and this will give me the radius of the circular curve. So how will I find out the length of the curve? It is nothing but length is equals to r into deflection angle in radians. This we saw it last week. Now, how will you find out the radius of the circular curve when a transition curve is provided? So when a transition curve is provided, its radius will not be the same. So before that, I want to come to this question. Before I do that, only then you will know, okay, how its radius is, how a transition curve is implemented. So in a transition curve, this is a straight section, this is a transition curve, and this is a circular curve. This straight section will have a radius of infinity, right? And this circular curve will have a radius of r. Now, within this transition curve, the radius of this section should vary from infinity to r. Okay, so this is achieved by many ways. There are many types of transition curves where, with increase in length, your radius will decrease. Okay, as you move along this length, the radius of this curve will decrease from infinity to r. Okay, so this is the main concept, but there are many ways of doing it, which you will you can do it in by using transition curve as a spiral curve. So this is a spiral curve, this is a lemniscate curve, or this is a cubic parabola. So if you use the equation of these curves as the equation of the transition curve, you will be able to achieve the radius transition from infinity to r. Okay, so these are the many curves that can be implemented for a transition curve. So what do you understand from this? You can understand that transition curve is not an arc of a circle like a circular curve. So what did we see simple curves as? Simple curve is simply, so if this is a circle, this the simple curve is simply an arc of the circle. Okay, so its radius will be constant throughout the circle. Okay, so this is for a horizontal curve. Now, by seeing the spiral, lemniscate, or cubic parabola, you can understand that transition curve is not a circular curve or not an arc of a circular curve, but it has a different equation. So when you find out, um, so when you come back to this question, come back to this question, okay, here the radius, it is the start of the, so let me take this as the start of the transition curve. Okay, its radius is infinity. Now this is the end of the transition curve, its radius is r. So radius is changing from infinity to r, which means this distance, right? This radial distance is not constant. It is changing with length of the transition curve. Now you are asked to find out the length of the circular curve, which means you have to find out the length of only this distance. Okay. You can, in order to find out the length of this distance, you have to find out the angle subtended by these two radial distances, right? Sorry, I'm not drawing it properly. Right? You have to find out this angle. Only if you find out this angle, you can find out the length subtended by this angle, right? This is the length that you want. So how will you find out this angle? This angle is not delta. Okay, like because delta starts from this tangent to this tangent. The angle of deviation between this tangent and this tangent. And this tangent starts from here. Sorry, from here. Okay, so the tangent is here. So this tangent starts from here. Sorry. Hmm. So this tangent starts from here to and ends here. So this entire angle will be my delta. So in order to find out this central angle, there is a formula. So this central angle will be nothing but delta minus 2 into phi. Where, so what is this phi? This phi is the extra angle at the edges. Okay. If from the entire delta, if I subtract these two phi, I will get this central angle using which I can find out the length of the circular curve, right? Now, how will I find out this delta? I mean, this phi. So let us take this triangle. Okay, I'm drawing only this triangle. This is my phi. This length is L by 2. Okay, a transition curve divided by 2. And this is R plus S. Okay, so at this point, it is R plus S. But you need about the center because this arc is about the center, right? So you have shift from in this side as well as on the other side. So if you're taking shift about the, so if you're taking about the center, it is nothing but this radius R plus shift by 2 because you have shift on this on both the sides and you need the radial distance to the center of this shift. Okay, so it is going to be R plus S by 2. Okay, so if this is R plus S by 2 and this is L by 2, I can find out phi, right? Because length of the arc is nothing but R plus S by 2 into phi. Now phi, just a second. Yeah, so I'm sorry. L by 2 is equals to R plus S by 2 into phi, right? So phi is nothing but L by 2 into R plus S by 2. So if I substitute for this, I will get the value of phi and I already know the deflection angle. So if the angle at the center will be deflection angle minus 2 into phi. So let us find out what phi is. So based on the equation that they have given, if I substitute for that, okay, L by 2 into R plus S by 2. So L is nothing but 42. 2 into R is 70 plus S shift is 1.05 divided by 2. So phi here is 17.061 degrees. Okay. Now I need the length of the circular curve. This is very simple, right? Now I have to find out the angle of the center portion, which is delta minus 2 into phi. This is nothing but 0.36, so I will write it in degrees, 20.878 degrees. Okay. So length of the circular curve will be, okay, this is my theta. Let me take this as theta. And this is r, right? So for the circular curve, the radius will be constant. curvature length will be r into theta in radians. Okay, so r is nothing but 70 into 0.3644, which is 20.8 to 878 degrees in radians, and this will give me 25.507 meters. So this is the length of the circular curve. Now moving on to the next question. The tangent length of combination of circular and transition curve. So what is this tangent length? Tangent length is nothing but the length of the tangent. They are asking you to find out the length of the tangent. Wait, let me take this. Okay, so they are asking me to find out the tangent length of combination of circular and transition curve. Okay, so this tangent length is nothing but just a second. Okay, I will tell you the equation, but I will tell you how it was derived in next session. I thought I had the derivation with me, but uh, I did not derive this by myself. Okay, so I should check it once. I should derive it and I should check it once somewhere. So I will just let you know the formula, and then I will tell you in the next session what this tangent length means and how this was derived. Okay, so for now, just remember that it is the so its formula is length of the transition curve divided by 2 plus radius of the curve plus shift into tan delta by 2. Okay, so if I substitute for this, what is the length of the transition curve? It is 42 divided by 2 plus RC is 70. Okay, radius of the curve is 70 plus 1.05 is the shift, and tan delta by 2, we know that delta is, sorry, tan theta by 2. Yeah. Okay, we just now we calculated theta. It is nothing but 20.908 divided by 2. Okay, so if you substitute for this, you will get 34.088 meters. Okay, yeah. Now moving on to the next question. So I told you, so we saw how this transition curve has to be achieved. So with change in length, its radius should decrease. Now there are three ways of doing it. As we saw, it can be spiral, lemniscate, or cubic. Now they are asking you in this question, what is of the three, what is recommended by IRC? Okay, so this spiral is also known as clothoid. Okay, and IRC recommends, of the three, IRC recommends clothoid as the length of the transition curve. I mean, as the type of the transition curve that needs to be provided. Okay, now let us come to compound curves. Okay, so this is a question about compound curves, and first let us understand what a compound curve is. A compound curve, so long we were talking about transition curves. Compound curve is a horizontal curve. Okay, it is in the main portion of the curve, not the transition curve. And we were saying simple curves all this while, which means this is the arc of the curve and the radius will be constant for the entire horizontal curve. So this is the entire horizontal curve, its radius will be constant. For a compound curve, for one portion of the curve, it will have one radius, and for the remaining portion, it will have another radius. Okay, so this is called as compound curve. Okay, now they are asking you what should be the length of the transition curve. Okay, now you may think what is new such that I have to find out the length of the transition curve. If you see for this compound curve, so transition curve is changing from straight section to curved section, right? So this will not have a problem. You will find out the length of the transition curve as it is. We know three formulae, we will substitute it and find out the length of the transition curve. Here also at the end you will find out length of the transition curve by using the three formulae. Now between these two curves you also you have to provide a transition curve. So these two is not a problem for you, but between the two horizontal curves you have to provide a transition curve, and that is what they are asking you to find. Now how will you find out this length of the transition curve, and why is a transition curve required between curves? Okay, so we saw transition curve is for gradual introduction of radius or centrifugal acceleration or extra widening or whatever it is, right? Now if so even in this compound curve, here in this portion it has a radius of r1, in this portion it has a radius of r2. Now what you have to do, you cannot simply change the radius from r1 to r2, right? So you have to provide a gradual transition, and that transition will be provided by this transition curve. Also for radius r1 it will have one value of super elevation. For radius r2 it will have another value of super elevation. Say for radius r1 the curve may be, the super elevation may be kind of less, okay, in this section. Now when you go to radius r2, since it is a very sharp curve, okay, since the radius is small, the super elevation, the pulling out of the vehicle, okay, will be more, and so the super elevation has to be more. Okay, so there is a difference in super elevation between the two curves in a compound curve. So in order to provide this transition from this super elevation to this super elevation, you have to provide a transition curve in between. Okay, so that is why a transition curve is required in between these two. Now what should be the length of the transition curve? Okay, so here you're starting from 0, you're starting from radius of infinity to radius of r1. Here you're going, if you're traveling this way, you're going from radius of r2. Okay, if you're going in this way, you're going from radius of r2 to radius of infinity. Okay, now you have to, so you know how to find out the transition curve for this, but here at this point you want the transition from radius of r1 to radius of r2, right? Or a super elevation of e1 to super elevation of e2. So in such a case, what you have to do is, already there's a distance. So let me say, if I have to find out the length of the transition curve for length of the transition curve for a horizontal curve of r2, this r2, and let me take it as one curve. Okay, there's no one more curve of r1. If I have to do this, I have to find out a transition curve for infinity to r2. Now for compound curve, already the radius of r1 has been introduced here, right? So infinity to r1 has already been done. Okay, so at this point, sorry, infinity to r1 has already been done, and r1 is maintained in this horizontal curve, right? Now I simply have to change from r1 to r2. So how will I do that? I can simply do that by finding out the transition curve required for R2, transition curve required for R1, and I simply have to find out the difference between these two, right? Only the extra distance is required to make the transition, right? So if I have to find out the transition length between these two curves, I have to find out the transition separately, length of the transition curve separately for these two curves, and then I have to find out the difference between the two. Okay, so this is what has been asked. Now mostly we will use the centrifugal acceleration criteria for this compound curve formula. Okay, length of the transition curve between compound curves. Okay, right. So we will substitute for what has been asked. Okay, a compound curve is designed for a speed of 75 kmph. The radius of the flatter curve is radius of the bigger curve. Okay, is 600 meters. Radius of the smaller curve is 400 meters. What did I mean by radius of the bigger curve is its radius will be flat. Okay, it is kind of flat. Okay, I did not mean bigger curve. I just meant the length of the curve can be small also. The radius will be large, which means it is kind of flat when compared to the other curve, which has a sharp curvature. Okay. Now, the length of the transition curve between the two is asked. We know the formula to find out uh, transition curve based on centrifugal acceleration. So this is nothing but V cube by C into R, right? C we know that 80 divided by 75 plus V. So that will give me 0.533. It is greater than 0.5, so it is okay to use this. Now LS, I have to find out for two. So I have to find out the length of the transition curve for two radius, right? For radius R1 and radius R2. So let me find out LS1. So that will be equal to V cube by CR1, which is 75. So which is 75 square divided by 0.53 into radius will be 600. Okay. Now let me find out length of the transition curve LS2, which is 75 square divided by 0.53 into 400. So which one will be the greater of the two? The denominator is more for LS1. So LS1 will be lesser and LS2 will be more comparatively. Okay, comparing LS2. So if you see LS2 will be greater than LS1. So you have to find out the difference between the two, LS2 minus LS1. So this will be 14.18 meters. Okay. But this is not the final answer, because for compound curves, there's one more rule, that the transition curve between these two curves has to be a minimum of 30 meters. Since the answer that you got is less than 30 meters, you have to give the answer as 30 meters, because you have to provide a minimum length of transition curve between the compound curves as 30 meters. Now, this has not been asked in any question. I mean, this is not there in the questions, but since we have talked about compound curves, I would also like to talk about reverse curves, which is more or less the same. There's only one difference. What are reverse curves in the first place? Reverse curve is, you have curve in one direction here and it will get reversed here. Okay, so here the radius, the center of the radius, center of the arc is here, and here the center of the arc is here. Right? Now, as we saw earlier, the transition curve at this end and this end will not have a problem. But in between the curves also, you have to provide a transition curve. Why should I provide a transition curve? even if it has same radius. So reverse curves can have same radius, right? Unlike compound curves, curves can have same radius, but they are in the opposite direction. Now you have to find out transition curve for these also, because for this portion, okay, where will the outward force act? Outward force will act here. Here the outward force will act in this direction, okay, which means when you travel on a horizontal curve, how will your super elevation be? Since it is pulling this vehicle outwards, its super elevation will be in this direction. The rays will be in one direction, in say left direction. Now, when you come to the opposite direction, the vehicle is pulled in this direction, right? Your vehicle will get lifted like this. So, in order to compensate that, in order to take care of that, the super elevation will be in this direction. See, it is in the opposite direction, exactly opposite. Here it was in one side and here it is in the other side. So what will you do? You have to first bring this to zero. So from this you have to bring it to zero and then raise it in the opposite direction, right? You have to bring it to a camber and then you have to raise it in the opposite direction. So what will you do here? You're going from r to infinity and then from infinity to r again. So this is nothing but entire length of transition curve you have to find for these two cases, and you have to add it up, right? Because here it is in one direction, the super elevation is in one direction, and here the super elevation is in other direction. So for you to reduce the super elevation from one direction to zero, okay, here it will be zero, and then you have to raise it in the other direction, right? So it is just like doing it for a normal transition curve, normal horizontal curve. The only difference is there are two curves adjust one after the other. So you have to find out transition curves for these two curves and simply add it up. So this is the difference between compound curve and reverse curve. So compound curves you have to find out the transition curve and find out the difference, whereas for reverse curve you have to find out the transition curve and you have to sum it up. Okay, so this is the difference. Okay, now moving on to gradients. So there are, so what is a gradient? It is in the vertical elevation, if you have to go from one level to the other, okay, you will connect it by means of a gradient, okay, and this will be represented by 1 in n, or it is represented by percentage, okay. So this is how gradients are represented. Now there are three three main types of gradients. One is ruling gradient. Okay, so what is ruling gradient? It is to decide the resisting length. What do I mean by resisting length? Okay, so when my vehicle tries to travel on this increasing gradient, okay, its motion will be resisted by the upward slope, right? But you have to take care that when you're traveling, so let us say this is a flat section, and after that you're traveling on this slope, okay. So this straight section, if you're traveling at a speed of say 60 kilometers per hour, when I when I move to this increasing slope, okay, when I move to this gradient, my speed should still remain the same, 60 kilometers per hour. Okay, you may ask how, but you have to provide a gradient in such a way that its speed is maintained. That speed is called as ruling gradient. Okay, so vehicles can travel on this grade without any reduction in its performance. So that is ruling gradient. Now after this there's something called as limiting gradient. Okay, so this limiting gradient, if you have no other go and you have to provide a higher slope more than the ruling gradient, then you will go for limiting gradient. Okay, um, okay. So if your topography, so in hilly areas, you cannot avoid it, but from one point to other, okay? If you you have to this is one level and this is at the other level, but this slope is greater than limiting gradient. Sorry, ruling gradient. Okay. Why? If I try to connect it by limiting gradient, okay. So if this is my limiting gradient, it is lesser. To reach this point, it will require a longer distance. Okay. And this will increase the cost of my project. So in order to avoid that, what will they do is they will provide, instead of ruling gradient, they will provide limiting gradient. Okay. And that is why a limiting gradient is provided. And there's one more thing called exceptional gradient. So this is for extremely short length. Say, if you are providing a gradient, usually you will not keep on providing the gradient. You will cut this gradient at some point and you will provide a horizontal curve. Okay. And then only if you want to raise it again, you will again increase the gradient. So this is what you will usually do. Now for exceptional gradient, the gradient is so high that this length is very short. Okay. So this you can provide only short lengths because this gradient is already very high. Okay. And your vehicle cannot travel like this for longer distances. So you will provide a short increase like this, and then you will provide one gradient at a limiting gradient or a ruling gradient. Okay. And then again you can increase it. So this is how, so this is what is called as exceptional gradient. Okay. And if you see, okay, so any road, so even in previous sessions, we would have seen that any road will have something called as a minimum gradient. Why this minimum gradient is provided? Because in order to um, facilitate the drainage. Okay, whenever it rains, the water has to drain out somewhere, right? So in order to, for such purposes, you will provide a minimum gradient. I have not shown this here. Since it is there in this problem, I would like to make a comment on this. So absolute minimum gradient for pedestrian paths is 0.3%. It is there in slides. You can refer to it. So based on these terms, we will see which is correct and which is wrong. Okay. Limiting gradient is used to design resisting lengths. Is it so? It is not the correct answer because it is ruling gradient which provides the resisting length, right? Now, next question is minimum gradient is decided based on drainage conditions. Yes, we saw that this is correct. Absolute minimum gradient, I already told you that it is not 0.5% but 0.3%, so this is wrong. Flatter gradients are desired on high traffic volume roads to ensure smooth and safe operations. So this, I actually wanted to show you those slides where these terms, these points have come, but I missed it. But just know that flatter gradients are provided for high traffic volume roads. So the answer to this is 2 and 4. Okay. So we have questions. We have 7 more questions. Okay. And this will require some concepts. Okay. So this maybe we will see in the next session. Okay. As of now, I'm concluding this session. Okay. As we are running short of time. Does anyone have any questions?
Thank you so much, madam. You have elaborated it very widely, madam. Being Vinay Chaturthi holiday, only 4 persons were there. Despite that, you took lot of effort and explained everything neatly, madam. Thank you so much. Very kind of you, madam.
Thank you.
Thank you, madam. Thank you very much.
Thank you. Thank you. Thank you so much. So if there are no questions, we can end this session.
We can close it, madam. Thank you very much.
Yeah. Okay. Thank you.